Okay, so now how do we predict this for any range of increase of pressure and temperature? Well, this is where we get to what's known as the Clapeyron equation. Okay, so here's my generic phase diagram, P versus T with phase alpha and phase beta, and the boundary between those phase diagrams is given by dP dt, right? Okay, so whatever this relationship is, P versus T, or the change in P versus the change in T, that's going to give me that boundary. Okay, so we start by noting that the chemical potential, I'm going to say chemical potential of phase alpha as a function of pressure and temperature has to equal the chemical potential of phase beta as a function of pressure and temperature. So all data points along this line have equal chemical potentials. We also remember fundamental equation, dG equals VdP minus SdT, okay? And we note that we can exchange free energy and chemical potential, right? We can make, they're the same thing when it's the molar Gibbs free energy. So now I'll expand on this relationship, okay? And I'll say that we're gonna go to molar quantities so that we can connect, remember, molar free energy equals chemical potential. So now if I look at the molar volume, and I'll just say molar volume of phase alpha times dP minus molar entropy of phase alpha times dt equals the molar volume of phase beta times dP minus the molar volume of phase beta times dt. So we just set those two things equal to each other, okay? And so now what I'm going to do is collect the like terms. So I'm going to do a little bit of algebra here, and I'm going to say Sm. So I'm going to add, oops, I wrote volume, but I meant to write entropy. Okay, so I'm going to collect the entropies and the volumes on each side. And when I do that, I get Sm of phase beta minus Sm of phase alpha all times dt. So add that over to that side, subtract V over to this side, equals molar volume of phase beta minus molar volume of phase alpha times dP. And I will note that this Sm of phase beta minus Sm of phase alpha, I'm just going to call that delta S of the phase transition, TRS, okay? So that becomes delta S dt, and this, of course, is delta V of the phase transition, dP. And what we're interested in, right, is dP by dt based on this graph. Okay, so if I collect those terms here, then what I end up with is, so divide dt over, divide V over, I get delta S of the phase transition divided by delta V of the phase transition equals dP by dt. And noting that delta S equals delta H divided by T, I'll make a substitution for delta S there. And this becomes delta H of the phase transition divided by T, and that's, of course, T at the phase transition, TRS, times delta V of the phase transition equals dP by dt, and this is the Clapeyron equation. So this gives us the boundary between any phase, right? So it says dP by dt equals delta H divided by T times delta V, okay? And then we note that this is reversible because we start by saying set the two chemical potentials equal to each other, okay? So I'm going to keep going. So let's